Hello, everyone! Welcome to today's Geometry Masterclass. Honestly, I am absolutely thrilled to have you all here. Today, we're diving deep into a topic that is just absolutely crucial for your exams, geometry. And we are specifically focusing on circles and tangents. We have 5 amazing problems lined up directly from our study material today. They're going to test your concepts and, more importantly, really sharpen your problem-solving speed. So grab your notebooks, sit up straight, get ready to focus, and let's make this learning session brilliant. Okay, let's dive into this.
All right, jumping right in, here is Section 1, Problem 1, Angle of Tangents. ध्यान दीजिए, pay close attention, because here is our very first fundamental warm-up problem. Now this one's a classic, right? It's all about the angle of tangents. It might look super simple at first glance, but it tests a core geometry property that you literally must have at your fingertips. So, from an external point P, 2 tangents, PA and PB, are drawn to a circle with center O. Now here is the golden key in the text. If the distance OP is exactly equal to the diameter of the circle, what is the angle APB? We have 4 options here, ranging from 40 to 60 degrees. Take just a quick second to mentally visualize that circle, those 2 tangents wrapping around it, and that center line OP. Have you got it?
Step by step, so much to hand. First, we identify our given property from the source. OP is equal to the diameter. That simply means the length of OP is 2r. Now remember your fundamental tangent-radius relationship. The radius is always perfectly perpendicular to the tangent right at the point of contact. This creates a beautiful right-angled triangle, OAP. In this right triangle, the perpendicular radius is r, and our hypotenuse OP is 2r. Basic geometry tells us that if the perpendicular is exactly half the hypotenuse, the angle at point P for that top triangle has to be 30 degrees. Since the geometry is perfectly symmetrical for both tangents, the total angle APB is just double that. So 30 plus 30 gives us a total angle of 60 degrees. Therefore, our final answer is option D, 60 degrees. It's simple, highly logical, and very important to know.
Excellent work on that warm-up. Now let's keep the momentum going. Here is Section 2, Problem 2, Direct Common Tangents. Moving right into our core exam topics, we are going to look at direct common tangents. Let me tell you, this is a topic that examiners absolutely love to test, and I want you to be completely confident whenever you see it on a paper. We need to find the length of the direct common tangent of 2 distinct circles. We're given our variables. The radius of the first circle is 10 centimeters, the second is 15 centimeters, and the total distance between their centers is 30 centimeters. Look at the options carefully. Can you mentally recall the standard formula for this exact scenario? Think about that distance between the centers and what we algebraically need to do with those 2 radii.
Let's walk through the calculation process together. We note our radii, 10 centimeters and 15 centimeters. The distance between centers is 30 centimeters. Now, the mathematical formula for the length of a direct common tangent involves taking the square root of the distance squared minus the difference of the radii squared. That means we calculate 30 squared minus the square of 15 minus 10. That translates to 900 minus 25, which gives us the square root of 875. If we simplify that standard root, it equals 5 root 35. Now check the options again. Do we see 5 root 35 anywhere? No way. So the correct mathematical choice from our source is actually option D, none of these. You know, what's really interesting about this is that none of these is a classic exam trap. You have to trust your calculations enough to confidently pick that option without second-guessing yourself.
And this actually brilliantly illustrates a major exam point that I need you all to remember. We just calculated a direct common tangent, but you absolutely must conceptually understand the crucial difference between a direct common tangent and a transverse common tangent. It prevents so much exam day confusion. Direct tangents run smoothly across the outside of the circles, staying completely on the same side of the imaginary line connecting the 2 centers. Transverse tangents, however, physically cross over that center line, making a big X shape right between the circles. The calculation formulas are different, the geometry is different, and mixing them up is a trap we definitely want to avoid.
Which brings us perfectly to Section 3, Problem 3, Transverse Common Tangents.
Let's transition directly into applying the transverse concept we just highlighted. This is going to lock in the difference perfectly. Look at this beautifully structured question. The final length of the transverse common tangent is already given to us as 24 centimeters. The radius of one circle is 16 centimeters, and the total distance between their centers is 30 centimeters. Our task? Find the radius of the other circle. I really want to emphasize that this is a reverse-engineered problem. The final length is given, but a core component, the radius, is what's missing. Let's see how we tackle this one together.
Let's verbally break down how to algebraically solve this backwards. The absolute crucial point is recalling the transverse common tangent formula. It's the square root of the distance squared minus the sum of the radii squared. We set our known 24 equal to the square root of 30 squared minus the square of 16 plus our unknown radius. By squaring both sides to remove that pesky root, we get 576 equals 900 minus that radius bracket squared. Rearranging this algebraically gives us the radius bracket squared equals 324. Since the square root of 324 is 18, we know that 16 plus our unknown radius must equal 18. And what does that leave us for the missing radius? Exactly, 2 centimeters. So our answer is option C. Great job following along with that algebra. It can get a little tricky.
Now, before we tackle our next problem, we need to quickly define a special geometric case: externally touching circles. This is a scenario where two circles just gently touch each other at a single point on their outer edges. In this very specific case, the total distance between the centers of the two circles is exactly equal to the sum of their radii. Defining this sets up the perfect foundation for our final two problems.
All right, let's use that foundation. Here is section 4, problem 4, externally touching circles.
Here is the question straight from our source material. Two circles of radius 4 centimeters and 6 centimeters touch each other externally. Find the length of their direct common tangent. I'm reminding you to apply that definition we literally just covered regarding the distance between centers. How can we use that fact to make solving this practically instant? Let's see how quickly this problem can be solved with the right conceptual approach. First, we identify the condition: the circles touch externally. We note the radii are 4 centimeters and 6 centimeters. Because they touch, we immediately know the distance between centers is simply 4 plus 6, which is 10. Now, while you absolutely could plug that back into the long formula, there is a heavily simplified standard shortcut just for touching circles. The tangent length is exactly 2 times the square root of the product of the radii. That gives us 2 times the square root of 4 times 6. The square root of 4 is 2. Pulling that out gives us 2 times root 6, which beautifully results in 4 root 6 centimeters. I absolutely praise your focus here. Recognizing that shortcut saves you precious time in an exam. Okay, take a deep breath. Here is our final boss for the day. Section 5, problem 5, the three-circle theorem. All right, students, we have officially reached the final, most complex theoretical question of today's masterclass. This is often referred to mathematically as the three-circle theorem. Let me read this carefully for you. Two circles with radii A and B, respectively, touch each other externally. Let C be the radius of a third, smaller circle that neatly touches these two larger circles as well as their common tangent. What is the mathematical relationship between A, B, and C? Look, I totally know reading this intimidating variable-based question can cause a bit of panic, but let me reassure you, it becomes remarkably simple once you recognize the geometric pattern.
Let's present the raw options exactly as they are provided in our source material. We're looking at various fractional equations involving our three radii. Notice how all the equations relate the reciprocals of A, B, and C. Interestingly enough, options A and C actually represent the exact same addition relationship in the source text. Option B uses a subtraction format, and option D kind of jumbles the placement of the variables entirely. Let's move to the solution and see how this builds your geometry toolkit. The correct relationship is option A. The standard equation is 1 over A plus 1 over B equals 1 over C. Let me emphasize something absolutely critical for all of you focused learners out there right now. Please do not attempt to derive this entirely from scratch during a timed competitive exam. Memorizing this specific fractional relationship is a massive time saver and is definitively a key takeaway from today's explainer. It directly leverages all those externally touching tangent formulas we just mastered.
You all have been absolutely fantastic today. Great energy. अगर आपको ये एक्सप्लेनर हेल्पफुल लगा हो तो प्लीज़ लाइक, शेयर और चैनल को सब्सक्राइब करना मत भूलना। सारे PDFs के लिए मेरा टेलीग्राम चैनल ज्वाइन करें, लिंक डिस्क्रिप्शन में है। Keep watching and stay tuned. But consider this before we completely wrap up. How would all these beautiful algebraic formulas we learned today change if the circles touched internally instead of externally? Think about that geometric shift, visualize it in your head, and stay curious.